All right, hello class, and welcome to lecture 13. So in this relatively short lecture, we will consider a special case of uncertainty. And you remember there was a quite great variety of them. In particular, we'll leave off the LFT for the moment and come back to it in lecture 14. And consider the special case where our uncertainties in our system parameters, or state space system parameters, have the form of additive, affine, polytopic, and interval uncertainties. So we have a nominal matrix. This applies to the B matrices as well, where we've got some nominal parameter, then some AIs, say 1, delta 1, plus da da da, plus a, let's say k, delta k, where these these uncertain parameters are affine, right, in our representation, which is actually a little bit unusual, but it's an important special case. And the parameters themselves lie in either the polytopic, right, so the convex hull of several points, right? So particularly, we usually take this to be the polytope. So the set of delta such that they add up to 1, and they're all positive, greater than or equal to 0. So an infinite number of possible values of the parameter in that case. And of course, the other case is the interval. And the interval uncertainty, and that's the case where all of the parameters lie in an interval. So delta minus to a delta plus. And those have an i's next to them. So actually, in point of fact, we'll consider both cases, of course, but actually we'll show that the interval one will reduce it to the polytopic one, and then we'll solve things for the polytopic one, actually. So the polytopic one is actually the more important one in this case, although the application applies to the interval as well. So we'll do this in two parts. So the first part will introduce a couple new notions. I hate to say of stability, but they're called stability, so I'll just call them stability. And that's robust stability. And the second is quadratic stability. So in the first part of the lecture, we'll talk about these two notions. And then in the second part of the lecture, part B, we'll talk about how to enforce them and how to use them to design controllers for these classes of systems. Obviously by LMIs. And I should just make a mention, right, of something here, right, which is that, and I'll talk about it again later on, in that unlike the optimal control part of this course, chapter 3 or 2, depending on how you're counting, robust control, these robust results really have no analog apart from the LMI framework. So the LMI framework is really a requirement to be able to study these kinds of systems. So the results that we'll give in this lecture really have no non-LMI equivalent, right? So the LMI part of this flavor or slant of this course is really actually necessary here, because there's just no way around it, and we'll see that especially when we get to this notion of quadratic stability. So we'll come back to that. All right. So in the previous lecture, we talked about the various flora and fauna of robustness and ways of parameterizing uncertainty in your model. And as I mentioned previously, in this lecture we focus on these very specific cases. So we're going to ignore these are all sort of LFT based. And in this lecture we'll sort of ignore it. There's only 14 slides, right? So it's a relatively short lecture. and consider a very important special case, so it's not a trivial special case, of these parametric, polytopic, and interval uncertainties. And I should say that while the results are limited, right, we can get them in 14 slides, they're relatively easy to state and relatively powerful, right? So they're relatively easy to enforce, easy to understand, and yet they give almost what I consider necessary and sufficient conditions for these cases. You know, we can debate on what we mean by necessary and sufficient, but very accurate, very strong results for these special cases. And that's why we go through them in their own lecture. So, all right, I'll move on then to getting to defining the class of systems. As I mentioned on the first slide, right, we have a nominal, where this is all in state space, right? So we could also have the inputs and the outputs as well, but we're not doing it quite yet. Now we just have the internal dynamics. Although we at the end of this lecture we'll extend these, right, to controllers and estimators, right? So don't think that we're just considering internal stability. Right. So if you have uncertainty in your B, C, and D parameters, right, they have the same form, right? So they depend on in an affine manner. Affine because there's a term which doesn't depend on delta, and then there's these linear terms which do depend on delta. So affine means linear plus a term which doesn't depend on delta. Linear would mean if the deltas were 0, the system matrices would be 0, but that's obviously not the case here. So we have two cases, as I said. We have the interval and we have the polytopic case, simplex polytope. And we'll consider them more or less in a unified way, right? So we won't actually consider them separately. So we'll focus on the polytope, and then we'll show that the interval case can be reformulated in terms of a polytope. But we'll get there shortly. Right. So the first big concept that we're going to talk about this lecture is that of robust stability. Right. The second one, by the way, is quadratic stability. But not in this slide, of course. Okay, so robust stability and quadratic stability are, I would call them labels. A system is not robustly stable. It's stable. It's stable or it's not stable. So it's stable for all uncertainties in the set, or it's not stable for all uncertainties in that. But that's not really what robust stability means. Sort of. Robust stability is a bit of a tricky beast. So basically, we say that a system, right? Let's say an A naught coupled with a set of uncertainties, right? We don't actually say what this set looks like, right? This may be interval, maybe polytopic, maybe something else. The definition applies regardless of what this set is. The definition applies to any class of uncertainty sets. Right. So we say that the pair A and delta is robustly stable, or stable over delta. Right? And if we don't say over what set, the term robust stability has no meaning. So it's robustly stable over delta if A plus delta is Hurwitz for all delta in delta. So that's important, right? The Hurwitz part of that is important to parse. So think about that a little bit. So it's not saying that anything about the trajectories of the system, right? It's not saying whether the solutions converge to zero or if they're bounded or anything like that. This is an algebraic definition, right? It's a representation definition, right? Saying something about the pair A and delta, not anything about solutions of an associated system. So it says basically for any matrix delta in this set delta, A plus delta has all negative eigenvalues, right? So that's negative eigenvalues. So that's important because, right, what do the eigenvalues tell us about a system? Well, they can tell us something. So for example, if the system is not time varying, and in the system definition is just A naught plus delta, then if A plus delta is Hurwitz, then the eigenvalues are negative. Then if delta is fixed, if it doesn't change over time, then that will in fact imply stability because it's just a linear system, and so the eigenvalues are negative, and so it's a static system, and so the trajectories converge to zero. So this implies stability if delta doesn't change. However, if delta does change, saying that the eigenvalues of A plus delta are Hurwitz, are negative, doesn't tell us anything about the solutions of the system, right? The trajectories of the system. So we have to be a little bit careful when we talk about robust stability because it implies stability only for a very limited class of situations, specifically those where the parameter delta is unknown but lies in the set delta. Right, this is the set. This is the matrix. Right. So what does this mean? So basically, if you remember what this means that if we apply the LMIs and the Lyapunov theory, right, that for any delta, any given delta, right, there exists a Lyapunov function which proves stability of that system, right? So that was a very old result, which says that if the system is Hurwitz, if the system is stable, there exists a Lyapunov function which establishes that fact, right? And this is true for a very large class of systems, even time-varying ones. But in this particular case, right, any particular choice of delta, this thing is Hurwitz, and so there exists for any particular choice of delta a P, a positive matrix, right, which we know how to find, that infinite integral, which proves stability of the system, which satisfies this Lyapunov LMI, Lyapunov inequality. Right? But what's important to note is, of course, that P may depend on delta, right? So the eigenvalues of A plus delta are going to be different for every possible choice of delta. And so the P that we get from solving that Lyapunov inequality is going to be different, right? So it's important to note that there's a dependence on P here, right? P of delta, right? And so that's important, right? It's important because now if we try and prove stability in the case where the parameter delta is time varying, that Lyapunov function doesn't work, right? So we have this Lyapunov function which depends on delta, right? And so if we try and use that Lyapunov function, well, delta is changing with time. So if we take the derivative of the Lyapunov function, v dot here, then, well, we get the normal parts of Lyapunov, but if we apply the chain rule to this, right? So this is a function of time, this is a function of time. Well, v dot is, right, x dot p of delta t, x of t plus the normal part, x p x dot of delta. And then, but there's a third term, because remember, all three of these depend on t. There's a third term, x transpose p dot of delta of t. Right. So that's this bit right here in the middle, a third part. And while this Lyapunov inequality implies that this part by itself is less than or equal to 0, we don't know anything about this part right here, right? Because the Lyapunov function is changing over time. So even though, right, for a given, at any given instant in time, right, the trajectories may be decreasing, or the value of the Lyapunov function may be decreasing, the Lyapunov function itself may be increasing, right? So that's a weird thing to do. So even though these trajectories are converging, right, the Lyapunov function may change its shape, right? So that, right, now maybe these trajectories are leaving in, right? So this is a problem, right? We have that this v dot is less than 0 plus this term right here. And if we can't guarantee this is true for all time, then we can't conclude stability, right? So that's an important part. So in general, if delta t is time varying, then we can't, robust stability does not imply stability. So robust stability does not imply stability if delta is time varying. So here, our first notion is that of robust stability, which is an algebraic condition on the eigenvalues over a set. Eigenvalues over a set. Not a definition of stability itself. It sometimes implies stability, but not always. Right? So a notion of stability which doesn't imply stability. That's the first one. First concept. Oh, sorry. What? Right. So our next notion is that of quadratic stability. I think I mentioned that. Right. So this also has stability in the title, right? So there's stability right there. But this notion of stability is actually even more problematic. Remember, we had systems, we had representations of the systems, and we had system properties, so system properties. We had properties of the representation, and then we had optimization, or LMIs. Sorry for my handwriting there. And sometimes we can use LMIs to enforce properties of the representation, which are then used to enforce properties of the system. Right? We talked about this in some depth in our section on optimal control. So what is this? What is quadratic stability? So let me just state what it is first of all, right? So we have a system, right? And quadratic stability is defined, well, in this case, just using A naught, as defined for the pair A naught, comma, the set delta, right? The uncertainty set, right? For a given pair of A naught and delta, we say that that pair is quadratically stable if there exists a p greater than 0 such that A plus delta transpose P plus P A plus delta is less than 0 for all delta in that set. Right. So let's take a step back and think about what this definition is asking of us, right? How it's defined. Is it defined in terms of the representation of the system? Well, the representation does show up. A shows up, and delta does show up there. But it's not a property of the representation per se, right? I can't take the eigenvalues of the representation and say anything about whether quadratic stability is satisfied. Instead, this notion of stability, this quadratic stability, is defined directly in terms of an LMI, right? An infinite dimensional LMI, one that has to be satisfied at an infinite number of points, but it's defined nonetheless as an LMI itself. Right? So a notion of stability which bypasses the whole representation thing and gets right into the LMI itself. So it's an LMI definition. It's really a definition of an optimization problem, not much less a notion of actual system properties, right? So definition of an LMI to enforce. So why would we label it stability? Does it actually imply any properties of the stability? Is it equivalent to any properties of the stability? Well, the answer is actually no. I mean, it implies stability if it's satisfied. But it's not necessary in any sense. Well, there are certain sets. There's actually a very important paper by Packard and Doyle where quadratic stability is shown to be equivalent to in certain circumstances, and unstructured uncertainty is shown to be equivalent to stability, right? Robust stability in particular. For a certain special case. Here I'll just use RS versus in a special case. I don't want to say that's true in general. All right. So, okay, let's think about this a little bit more, right? So it's an optimization problem, which is hard to enforce because we have to enforce it in an infinite number of points, every point in the set. So obviously not. So what's called an infinite dimensional LMI at this point, because we haven't shown how one could actually. We can't just plug this into YAML, right? It's not possible. All right, but it's an LMI, and let's think about what it means. Well, we know that, right, these P matrices, these positive P matrices, typically correspond to Lyapunov functions, right? So there's a Lyapunov function associated. If this LMI, infinite dimensional LMI, is feasible, there's an associated Lyapunov function, right? And what it's saying is that there's a single Lyapunov function, one that doesn't depend on delta. And such that if we take the derivative of the Lyapunov function, right? Derivative of that Lyapunov function, unlike in the case of robust stability, that derivative will actually be negative, no matter what delta is doing, right? Even if it varies, delta goes all over the place, right? Delta t, even if it looks like that. So you just take the time derivative, right? And because p doesn't depend on time, right? We just get our x dot terms, right? Right, and we just plug in for x dot, that goes there, that part goes, actually nope, that's right. Got the right sides there. And then there's no third term, right? So what this really means is that there's a single Lyapunov function, which is always decreasing no matter what the value of delta takes, right? So that's interesting, right? A single Lyapunov function which works for every possible value of delta. Now, as we know, right, as we've learned, right, a given system has a unique Lyapunov function, right, which proves stability of that system, right? There's a one-to-one relationship. Lyapunov functions are the one thing, right, that you can use to represent the property of that system, being stability in this case. Now we're having one Lyapunov function which is working for all values of delta. Well, if delta is varying very fast, well, that may not seem like such a it could be any parameter at any time. But still, it's worth noting and comparing to, say, the case of mixed H2 H infinity control, right? Where we were also using a single Lyapunov function to find or optimize over the H2 and the H infinity norms. So that's another case. So in general, aside from this very special case in Packard and Doyle, the concept of quadratic stability is not actually a concept of stability. It's a LMI. And that LMI, yes, it does enforce stability, but it's conservative, right? In the sense that there are certain systems, and I'll give one on the next slide, which are stable, but not quadratically stable, right? Even in the case of polytopic uncertainty, where we have no limit on the rate of variation, it's still conservative. Right? So let's take a step back here, right, and think, right, why we're doing this. So we've got an LMI, right? This is an LMI condition. This quadratic stability is an LMI condition. And whereas for robust stability, right, that condition was defined as, in terms of eigenvalues of the representation, Hurwitz of A plus delta, the quadratic stability notion is defined directly in terms of the LMI, right? And in both cases, right, we can go from that definition of robust stability to a system property in the case where we don't have time-varying uncertainty. And in the case of quadratic stability, we can also go to a system property. But in this case, we don't go through this intermediate step of properties of the representation. We go directly to system properties. Right? It's a direct form of analysis. And it's worth emphasizing that there's no notion of quadratic stability which is not defined in terms of an LMI. Right? Quadratic stability is a notion unique to LMIs, right? There's no version of this which you can use analysis and representation tools for. And part of the reason for that is, of course, representation tools use eigenvalues. And if your system is time-varying, eigenvalues don't tell you very much, right? In fact, the eigenvalues of a system are not really even defined for time-varying and nonlinear systems. We don't really have a notion of eigenvalues, although there are certain extensions. Right? So this is interesting, right? We have two notions of stability: robust stability, which doesn't imply stability, and now quadratic stability, which does imply stability, but is actually not equivalent to stability in any sense. So we can see that more clearly on the next slide, right? So this is just a repeat of the definition of quadratic stability, right? So nothing new there. Right? Where it's actually, this is an example of a system which has very little structure, and which is stable. So there's a stable system. I won't prove it's, I do prove it's actually stable. So it's a stable system. You can prove it's stable using a Lyapunov function, this Lyapunov function here. Right? So it's this Lyapunov function. We'll come back to when we talk about maybe hybrid systems later. We'll talk about this in a little bit more depth where it comes from. But this is the so we have basically two Lyapunov functions, v1 and v2, and the actual Lyapunov function is the max of those two. So it obviously depends on the state. You just calculate both of these two terms, and whichever is larger, that's your current value of the Lyapunov function. And in particular, these are the two values of p that we use. Right? So here's your system, right? It's this polytopic uncertainty, right? Right. So no additional structure to it. Polytopic uncertainty. We have no limits on the rate of variation, however. And yet the system isn't stable. Is not quadratically stable. So it's stable, it's a polytopic uncertainty, but yet it's not quadratically stable, right? So this is definitive proof, if you like, that quadratic stability is, in general, at least in the case of polytopic uncertainty, not equivalent to stability in any case, right? There is one case, it's not this case, not polytopic and not interval uncertainty, which are the subjects of this lecture, right? So we have two notions, robust stability, we have quadratic stability. Quadratic stability generally implies robust stability. Robust stability does not generally imply stability. Quadratic stability generally does imply stability, but it is conservative in that there are systems which are stable but not quadratically stable, even in the limiting case of polytopic uncertainty, which we consider here. Now, in the second part of this lecture, we will come back to the question of how to actually test quadratic stability and use it to do things like controller synthesis and some rather straightforward applications. Because remember what this is. This is a infinite dimensional LMI, right? It has to hold at every value of delta alpha in this parameter space, in this uncertainty set. And so there's no way to just plug this into YOMIP and check this stability condition, right? This is an LMI condition. This is an LMI condition for every delta A, but we would need an infinite number of them, a continuum of LMI conditions if we wanted to enforce it for all delta A in delta, right? Now, in the special case of polytopic uncertainty, and in the special case of interval uncertainty, we will give LMIs. We will show how to formulate an LMIs which are finite and which allow you to check this condition. But these are special cases. And in general, when your uncertainty set looks different, if it's norm-bounded, for example, these results will not hold. However, they do hold for these two particular cases, polytopic and interval. And so in the next lecture, we'll give those LMIs which enforce this constraint and then extend that to controller synthesis. So I'll stop the lecture there and come back next time giving those results.